obviously with respect to the two norms. Okay. Now I am going to prove an abstract result, and that abstract result says that if you have a bounded operator whose domain is a dense subspace of some normed space, then that bounded operator has a unique extension, okay, which is, so in other words, you're going to get a new operator which is the extension of the previous operator, but that new operator is defined over the whole space actually. Okay. So if I can prove this result, then since this is dense in L2R and this is bounded, so I can have an extension of this operator from L2R to L2R, and I can separate it like that. Okay. Basically, I wanted to prove the result that I am presenting now, this abstract result. But so now I am proving this result because of a need actually. Okay. Otherwise, this result would be kind of an abstract result, which apparently has no application, but it has lots of applications. Okay, so here's the theorem. It's a pretty abstract theorem. So it says that let E be a normed space. This is not difficult. So let E be a normed space, and E naught subset of E be a dense subspace. Okay, so it's dense in E. Further, let E naught is an operator from E naught into F. Okay, where F is another normed space. Okay, which is linear and okay. Then T naught extends, I would say then there exists a unique extension T of which is a map from E into F. Okay, unique right extension T of T naught such that this T is linear and bounded. Okay, and finally this T has the same norm as T naught. It has all these beautiful properties. Okay. So in other words, if you have an operator which is defined on a dense subspace and it's linear and bounded, then you can extend that operator to the whole space, and the linearity and boundedness is preserved. Even the norm of the operator is preserved. And obviously, if we prove this result, as a corollary of this result, we're going to get Fourier transform as what? As a linear bounded operator from L2R to L2R. Okay? And hence, we can use it in quantum mechanics. Okay. So, let's do the existence. What do you mean by extension actually?
Images.
By extension I mean
Domain extension.
that T, whenever f is from
E
E
naught.
naught,
Same as T naught.
behaves as T naught is. Okay. But when f is in
E naught.
E naught actually. So on over E naught, T and T naught are indistinguishable. Yeah. So let's take f from E. What do you think? What should be the next step? Exactly. So since E naught is dense in E, so there exists a sequence Fn, okay, in E naught, such that Fn converges to F in the norm of En. Okay? E as n goes to infinity, obviously. As n goes to infinity. What should be the next thing? What should be the next thing? What do you think? Now, since this is a convergent sequence and E naught is a bounded operator, linear bounded operator, so as T naught is, okay, belongs to the, it's a linear bounded operator from E naught into F, okay, so T naught Fn converges to
T naught F.
T naught Fn. Okay.
F belongs to E, then T of so T naught can be only operated on the E naught subspace, but not on whole E.
Ah, okay. Okay, this is a good point. That you can't operate T naught on
F.
Fn.
Then you operate on subspace.
Alright. So it converges to something. So it converges for sure actually.
Yes, sir.
Okay, it converges for sure. So it converges to what? So if Fn is converging to F, okay, then T naught of Fn converges to something. Okay. I don't know what that would be. Okay. So what I am doing next is basically this. So this is a good point. Thanks for this one. Okay. So I'm saying define something. Define an operator T when it operates on F. It gives you what? It gives you the limit and goes to infinity of T naught of Fn actually. So I don't know that it converges to something, but I'm assigning that limit to which it converges as Tfn. Okay. And what? Now if I'm defining T in this way, I'll show that this is well defined. Okay, so we're going to show next that T, which is a map from where to where? So it's a map from E now into F is well defined. Okay, it's well defined. And by well definedness, I mean uniqueness actually. Existence is there. The only you need to show the uniqueness. In other words, this limits exist actually. So and which belongs in obviously in F actually. So existence is not a problem. So here for the well defined end you need to show the uniqueness. Okay. Especially. So what does this mean? This means way he defines how maybe interprets this Fn is that basically is showing that this T naught of Fn is a Cauchy sequence. To see this, it says that, okay, so it's, do we need to prove that this limit must exist? Because you have a result, I don't know why he's proving it. There is no need to prove it. The existence of this limiter. So if T naught is linear bounded, okay. Okay, so you can have
We are showing density in maybe F.
you can have a critique over this argument of the existence that we were giving to this, because that result that the convergent sequences are mapped onto the convergent sequence is true for the linear and bounded maps between two non-displacable. While for E naught we only know that it's denser. Okay, it inherent norms from E. Okay, the argument is going to be essentially same as what we call this. It's not going to change. So in other words, the first of all, I'm going to show that this T naught of Fn, okay, is Cauchy sequence. Okay, and it converges to unique limit. So it's Cauchy, so it must be convergent and converges to unique limit. So in order to show the Cauchiness of this, what we need to do? We need to compute the T naught of Fn and T naught of Fm,
which is same as T naught of Fn minus Fs.
which is same as T naught of Fn minus Fm.
Fn
But
is
since this
convergent.
operator is bounded, so I can estimate this by norm of T naught times
Fn minus
Fn minus Fm, but this goes to 0
as n goes to infinity.
as n goes to infinity, as n comma m goes to infinity, because this sequence is convergent as
Convergent, so
Cauchy.
it is Cauchy.
Okay, so okay, so what does this shows? Okay, is there? Okay, we are missing an assumption. We are missing an assumption. The assumption is, we are missing an assumption, which is a key thing to do. So whenever you read, you should read it correctly. So we are having this trouble. So it's a Cauchy sequence, but what's a guarantee? Cauchy sequence in F, but what's a guarantee that it must converge?
Must be complete space.
So F must be complete actually. So F is a complete. So we need to add this assumption into what we call list factor. So now I can say that this shows
T
that
naught
T
Fn
naught
is
of
convergent.
Fn
E complete होना चाहिए.
is Cauchy linear.
E must be complete. Fn minus Fm must be
E must be complete.
E naught is
E
density.
the choker.
No. Convergent is Cauchy always. Convergent is Cauchy. It's the Cauchy for which we need convergence actually. So you don't need completeness of it. Okay. But I need completeness of Fs. So it's Cauchy
And F is complete.
and hence convergent.
And
Hence convergent, that is, now I can say that this limit n goes to infinity T naught of Fn exists. Okay? This limit exists. And if this exists, would that be unique?
Yes.
will that be unique?
Yes, sir.
We can show it explicitly. Okay? We're going to say that suppose there is some Gn that converges to f as well. Okay? There is some Gn that converges to f as well. So if this is the case, what's going to happen? I can say that, consider this, T naught of Gn and T naught, the difference of T naught of Gn and T naught of Fn. Okay? So what are you going to get? So this must be same as T naught of
F minus G.
Fn minus
Gn.
Gn, and that goes to 0. Okay? That goes to 0 as n goes to infinity. Okay?
बराबर दिया है
Why this goes to 0?
linear operator है
Okay.
otherwise Gn
I need to make it a bit more precise. So if Gn is converging to f
Fn is also
and Fn is converging to f,
n must be 0.
so Gn minus Fn will go to 0 basically. Because this will converge to f minus f, which is 0.
सही बात है
Okay? Okay?
Yes.
Now, since Gn minus Fn is going to 0, and T naught is a bounded operator,
zero zero पे
so
zero
T naught of Fn minus Gn will also go to 0. So this is what that
And sir, Fn and Gn are not equal, right?
they are not necessarily equal.
So sir, T of F is also limit of n tends to the of T of Fn, and T of F is also same as limit n tends to the
Okay. What does this uniqueness is showing actually, or maybe this argument is showing, that this limit or this T of F is independent of choice of the sequence that approximates f actually. So in other words, no matter what sequence you take which approximates f, you're going to have always the same limit, which is T of F. So here you are kind of showing the independence. Okay, so here you showed the uniqueness, now you are showing the independence. You are saying that, okay, imagine that there is another sequence, which goes to, which converges to f. So their difference will converge to 0. And, then the difference of these limits, obviously I should write as n goes to infinity, is going to get to the 0. In other words, as n goes to 0, the difference of the limits is not going to be, there's no going to be difference in between the limits actually.
they are same
And hence this is going to show that this mean is really well defined. So first, this exists,
and unique
and it's unique as well, no matter what sequence you choose that approximates your function. Okay? So we have this operator. Okay? So what properties this operator should have actually? So we showed existence, we need to show uniqueness, okay? We need to show its linearity, boundedness, its extension, and that its norm is equal to its norm, the norm of T. So this is what I would like to show. What should I do? So I get rid of this. Let's not get rid of this. Let's get rid of this statement from here. Okay? Okay? So hence, what does this show? That T from E to F is well defined. How can I show extension? How can I show that T is extension of Tn? So for that I need to take F from E naught. So give me a sequence that approximates f actually.
Itself.
In
Self
E.
of n in this.
Take itself actually. Okay. So take Fn equal to f for all n. So constant sequence actually. So what does this show? This shows that Tf and T naught of f is equal to each other. So the Tf is what? So the Tf is the limit n goes to infinity of T naught of Fn actually. But this is same as
T naught of
T naught of Fn.
right? On the outside E naught comes.
So for all f in T naught. So this shows that, what does this shows? This shows that T extends T naught. T extends T naught. Okay? How can I show linearity? What do you think? So for that I need to show that the T of AF plus BG, where F and G are from E and A and B are some constants, what you should have. So we know, that for F there exists Fn such that approximates F. Okay, so there exists some Fn that approximates F, and there exists a Gn that approximates G. Then by the properties of the limit, okay, so we can say that AFN, and these Fn's are in T naught actually, we need to be careful. Okay, so AFN plus BGN is an elemental E approximates AF plus BG. Okay, so this is equal to this. So what does this mean? This means that T, so I can say, this is the case, then I can say that this is equal to the limit n goes to infinity
T naught of Fn.
T naught of
Alpha.
AFN plus BGN actually. But T naught is linear, so I can take it inside. Okay? Take it inside.
And also
So this would be equal to, you apply the linearity of the limit, this would be equal to AF, simply, no, not AF but AF plus B. Yes, it is linear. Okay. How about boundedness?
limit by सही है that sum of limit of sum apply yourself.
Sum of the limit is the limit of sum. How about boundedness?
Absolute of limit is limit of it.
Yes. So for the boundedness, we need to take TF actually. So the TF is what? And this is an F norm. So it's limit n goes to infinity T naught of F. Okay. Norm is a
Continuous.
good guy. It's a continuous map, so I can pull this out. Okay. T naught of Fn. Yes. And what?
T naught is bounded.
So I can estimate this by limit n goes to infinity
Some number
of norm of T naught times norm of Fn. Are we doing something good?
Yes,
Yes,
sir.
sir.
And applying limit we have
To Fn directly. That's pretty good.
So what are we gonna get?
then T
You
naught
get
times F. Now
Why are we gonna get that? Oh, okay. So
norm is
this is less than or equal to T naught of
F times F.
norm of
Norm
Fn.
of F.
Okay. And what does this show?
T
This
naught
shows that
is bounded.
it's bounded up. Additionally, this shows that if I divide basically this by,
The
so
norm
it's going to be
context
the norm of T is less than or equal to
T naught.
norm of T naught, while this thing is obvious actually. This is obvious. Why? Because T is extension of T naught. Okay. So
सही
in
है.
other words, this guy This thing follows from above calculation,
सही
while this is trivial.
at least less than 12 inches.
That's
This is trivial.
I think that
Can't go beyond this because T naught is T is extension of T naught. So this completes the proof of the theorem. Okay. So what does this beautiful theorem is telling me? This beautiful theorem is telling me that if you have a linear boundary, and you can already see the beauty of what do you call the density. That is, the dense subspaces are really important actually. Okay, because it preserves lots of things. You want to do something in whole space, just do it in dense, and the same thing would be, it could be done easily. So what does this theorem is telling me? This theorem is telling me that if you have a linear bounded operator, okay, which takes the values from a dense subspace of a normal space and spits them out into a Banach space, okay, then that bounded operator, which is defined on dense subspace previously, can be extended to the whole subspace.
So unique extension.
Unique extension. You have to have a unique extension actually.
Extension is unique. ये हमने ये कहाँ पर show है?
We can,
We have shown there is extension or वो same है.
Unique.
what you are showing here.
Is well definedness of the map.
Try to figure out the unique.
Okay sir.
Yeah.
take
ठीक है.
सही है.
Okay. So what is the immediate application of this abstract theorem? The immediate application of this abstract theorem is that we had first the Fourier transform, okay, of a function as an operator, was linear and bounded operator from L1R into the space of continuous function which vanish at infinity. Then you have this Banach identity. Banach identity which says that if f is a continuous function with a compact support, then this equality holds. This equality holds. So I can interpret the Fourier transform, which was previously from L1Rn to the C0f, using this identity. I can interpret f as a Fourier transform, f as a linear bounded map from space of continuous function from compact support into the Hilbert space L2 of R actually. Okay. Now, since this map is linear, now we know that this space of continuous function with the compact support is bounded in all LP spaces where P is from 1 to 1, bigger than or equal to 1 but less than infinity. Okay, is dense in L2R. So you have an operator which is linear and bounded on a dense subspace and throws the values into a complete space, Hilbert space or a Banach space actually. Then, by this theorem, this f has a unique extension, which I am going to denote again by the same f actually. Okay. So this f has a unique extension, which is the Fourier series. Okay. It takes values from L to R to with 2 norm into
It's
L to R
with 2 norm.
with 2. So this is a kind of a giving the justification, the theoretical justification to the Fourier transform on L2. You can do something similar on LP. You need something similar. Okay. And okay. So that's kind of an immediate application of this abstract. Okay. So how much time do we have?
सही
We
बात
have
मान लिया.
a few minutes.
Yeah.
So in
सही बात
this,
मान लिया लेकिन.
Yeah, sir.
in these few minutes, what I'm going to do, I'm going to take 5 minutes and I'm going to tell you the exercises basically that you have to do.
Yes, sir.
Okay? Not going to do anything else. So this completes this chapter like this. Okay? So I haven't covered everything from this chapter, but I have just hit kind of the important bits from this chapter number 9 actually. Then you have what do you call chapter 10 and chapter 11. Okay. They are not